All right, part 2 of section 3.6. Here we're going to focus on derivatives of inverse trig functions. So to start off with, I'm just going to kind of go over what they are, because you haven't really done much with them since trig. Well, maybe, I don't know. But let's say that we have a function y equal to sine of x with the appropriate domain restriction, which for sine of x would be negative pi over 2 less than or equal to x, less than or equal to pi over 2. The reason we want that domain restriction, like from last video, is to ensure that the function whose inverse we're taking is 1-to-1, so that the inverse works out to actually be a function. So, big thing I want to point out is that when we are dealing with something like y equals sine of x, the input, that's the x, is an angle. Right, you take sine of an angle and you get out a ratio. And by ratio, I could mean a couple of things. When you very first learned this in geometry back in high school, you learned that sine, cosine, tangent are all ratios of sides of a right triangle. Right? But when you took trig, you learned about the unit circle and how if you take sine of an angle or cosine of an angle, that the result is the ratio of a coordinate to either another coordinate or a ratio or the radius of the unit circle, which is 1. So either way, for sine, cosine, tangent, all the other ones, cosecant, secant, cotangent, the input is an angle, the output is a ratio. For inverse sine or arc sine, you may also have seen it written as sine inverse of x. It's the opposite, right? So here, the input, or the x, is a ratio. And the output is an angle. So, important concept here is that arc sine of x is an angle. Arc cotangent of 5/3 is an angle. Arc tangent of 1 is an angle. So we input a ratio, we get out an angle, and that is the very nature of what inverses are. The inputs and the outputs swap. One side note here, very important, is that when you see this notation, that is not 1 over sine x. No. That is not cosecant x. That is arc sine x. All right, and this goes back to the idea that inverse and reciprocal are not the same thing. Remember, reciprocal is when you have a fraction and you switch the top and bottom. Inverses are when you switch the input and output, the x and the y, just like we see here. So it's important for us to kind of have that idea in our heads before we get into derivatives. And one last thing before we get into derivatives is actually using these notions of what's an angle, what's a ratio, to evaluate things like, for example, cosine of arc sine of x. So we know that arc sine of x is an angle. Angles we usually denote using the Greek letter theta. You could use other Greek letters depending on context. All right, but arc sine of x is an angle, and we want to evaluate cosine of that angle. So the thing is here, we can actually take this expression, cosine of arc sine of x, and write it entirely without trig at all. And the reason I want to review this is because when we take derivatives of inverse trig, the way you typically see it written and the way you're usually expected to give your response does not involve trig at all. So How do we do that? Well, it all goes back to drawing a right triangle. All right, and then labeling our angle arcsine x as theta. And I could have chosen that angle or the other one that's not a right angle. It doesn't really matter. I typically prefer the one I marked. But anyway, we know that theta is equal to arcsine of x. That means that sine of theta is equal to x. So I basically rewrote theta equals arcsine of x in a different way. These two equations that I wrote here are equivalent. They're saying the same thing. Now, since we have a right triangle in front of us, we're going to go back to our geometry class SOHCAHTOA definition of sine. We know that that's going to be the opposite side over the hypotenuse. So for this to make sense, I'm going to need to write x as a fraction. I can always write it as x over 1. So what that tells me is that the opposite side from theta is x, and the hypotenuse, which is always across from the right angle, is 1. So to figure out this other side here, because I'm going to need this one to find cosine of theta, I can use my Pythagorean theorem. So I want to know this guy before I can answer the question. So setting up Pythagorean theorem, we get x squared plus question mark squared is equal to hypotenuse squared. So if I do a little bit of algebra, then this is the result. I'm not going to consider the negative square root simply because we're talking about side lengths of a triangle, and without the context of a coordinate grid, that doesn't really make sense. So we're just going to leave it at the positive square root of 1 minus x squared. And now that we've figured that side length out, we can figure out cosine of arcsine of x. So cosine, if you remember from geometry class, is adjacent over hypotenuse. Adjacent is just a fancy word that means next to. So the side adjacent to theta is the square root of 1 minus x squared. And the hypotenuse, again, always across from the right angle, was 1. Fully simplified, our answer would be 1 minus x squared. And we can do this pretty much with any permutation of trig functions. The only important thing is that the inside, the argument, is an angle, meaning it has to be an inverse trig. So now that we've had a bit of a review over inverse trig functions, let's talk about their derivatives. So I'm going to go through a derivation on 2 of them and then kind of just give you the rest. So let's start off with arcsine. So let's say that we have a function y is equal to sine of x, and we want to know the derivative of y inverse. Well, to find the derivative of y inverse, there's a couple of different approaches I could take. We learned that rule last time that the derivative of an inverse is the reciprocal of the derivative of the original evaluated at corresponding, so switch x and y. All right, and remember when we switched x and y, I always wrote y inverse because that's what that would have to be. Well, we know what we know what y inverse is, right? If I were to ask you what is the inverse of sine of x, we would emphatically say arcsine of x, and not cosecant. Right, so with that, we know that y inverse prime is going to be 1 over cosine of arc sine of x. Well, for us, we actually already know what that is. Right, you see, we back up here in our review actually found out what cosine of arc sine of x is. We know that it's equivalent to the square root of 1 minus x squared. So I could rewrite this as 1 over the square root of 1 minus x squared. And ta-da, that is the derivative of arc sine of x. If I go through a similar process, I will find that, let me summarize what we just found here. Right, that's first one. Now, if I were to go through a very, very similar process, I could find the derivative of arc cosine of x. And to save us a little bit of time, I would get negative 1 over square root of 1 minus x squared. And that negative comes from the fact that when I take the derivative of cosine, I get negative sine. So that's why we have a negative there. But the process is exactly the same, bar derivative of cosine is negative sine. So you'd be taking negative sine of arc cosine of x, which, yeah. Okay, now I mentioned there was another way that you could have done this if using the inverse rule didn't make a lot of sense to you. And I'll use that to go through and find the derivative of arc tangent of x. So let's say that we have a function y equals tangent of x. And again, we want to know the derivative of y inverse. Okay, so the other approach is to go back to when we talked about just at the beginning of last video what inverses were and how to find them algebraically. Remember, the idea is that we had to swap x and y. Right, and when I place the y, remember I don't write y, I write y inverse. So now that I've done that, we can actually use implicit differentiation to solve for y inverse prime. So implicit differentiation, we're going to take the derivative with respect to x of every term in that equation. On the left side, derivative of x is 1. And on the right side, we'll have to use our chain rule. So derivative of tangent of stuff is secant squared of stuff multiplied by the derivative of stuff. So if I want to find y inverse prime, all I need to do is divide both sides now by secant squared of y inverse. Right. And if you remember your trig identities, you remember that 1 over secant is equivalent to saying cosine. So basically this is cosine squared of y inverse. Well, if y is tangent of x, we know exactly what y inverse is. We know it's arctangent of x. So essentially we need to find cosine squared of arctangent of x. And from there we can do our little triangle trick again. Right, so technically we did this in the last example, we just did it before the example. So whenever you're deriving these, you do have to do the triangle setup every time, but more on that in a second. So first, remember that arctangent of x is an angle. We're going to call that angle theta. So theta is equal to arctangent x. Remember, equivalently, that means tangent of theta is equal to x. And since we're going to use a right triangle, we'll go back to our SOHCAHTOA definition of tangent, right? Tangent is opposite over adjacent. So I would need to write x as a fraction, x over 1, which means when I go to set my triangle up, the side opposite from theta is x, the side adjacent or next to theta is 1. So I still need to get my hypotenuse, which I can do from Pythagorean theorem. Spare you the setup, it's going to be the square root of 1 plus x squared. So that is the triangle setup. Now that I have all three sides, I can find cosine of the angle theta. We know cosine is adjacent over hypotenuse. And whatever we get, we have to square it. So adjacent to theta, we have 1. And the hypotenuse was the square root of 1 plus x squared. Now when I square a fraction, remember you're squaring both the top and the bottom. And 1 squared is 1. Square root of anything squared is just the inside. So in this case, 1 plus x squared. And that is the derivative of arctangent x. So what we've just discovered is that the derivative of arctangent x is 1 over 1 plus x squared. And if you go through a very similar process, you would find that the derivative of arccotangent of x is once again just the negative of arctangent's derivative. So negative 1 over 1 plus x squared. I'm not going to go through the derivation of secant and cosecant. Quite frankly, I don't really focus on it in the homework or in the exam, but I do want you to see what they are, right? So that if you decide to look this up on the internet later, you know what is fact and what is fiction. All right, derivative of arcsecant x. It's 1 over the absolute value of x times the square root of x squared minus 1. And for our cosecant of x, it's just the negative of that. So negative 1 over absolute value of x times square root of x squared minus 1. So that combined with what we discovered earlier gives you all of your inverse trig derivatives. Side note, you do not have to do this derivation every time you take the derivative of an inverse trig function. It's important for you to remember all of these forms for inverse trig. So way I like to remember it, arcsine and arccosine, you have the square root of 1 minus x squared in the bottom. With arctangent and arccotangent, it's just 1 plus x squared. There's no square root. With arcsecant and arccosecant, you have the absolute value of x, and it's the reverse order of arcsine and arccosine, x squared of x squared minus 1. And then, of course, arcco anything will have a derivative that's just the negative of arc regular thing. So arccos have negative derivatives, arc regulars have positive derivatives. And these are just the forms, right? Once you know the forms, like I said, you do not have to do this derivation. That is going to cost you a lot of time if you try to do that. So let's look at 2 examples, just so you can see what I mean. First example, let's say we want to know the derivative of 9 arccosine of x over 3. All right. So to do this one, I'm not going to do any kind of weird derivation. I'm just going to go straight to the derivative form for arccosine. So I know that that's going to end up being, well, we have the 9, that's a coefficient, so we can put it outside. We know that the derivative form is negative 1 over the square root of 1 minus stuff squared. In this case, the stuff is x over 3. And we have to multiply by the derivative of stuff. Derivative of x over 3, well, x over 3 is 1/3 x, so its derivative is just 1/3. Since I have this 1/3 multiplying, I can bring it out with the 9, and we would get 9 divided by 3, which is just 3. So we have negative 3 over the square root of 1 minus x squared over 9. So I went ahead and squared x over 3. That's x squared over 3 squared. There we go. Which would be the answer, except it's important for us to simplify this one, because when we do this backwards, when we talk about integrals, a lot of times you're not going to be given that form to start with. So when I say simplify, I mean I don't want any fractions within fractions. So I need to get rid of that 9. But here's the thing, it's under a square root, so I have to multiply by 9 to clear the fraction. But that 9 needs to be under a square root as well, otherwise that's not what's going to multiply x squared over 9. And remember, you cannot multiply just on one side of a fraction, because you're only technically allowed to multiply by 1. So I have to multiply both the top and the bottom by the square root of 9. In the numerator, that's going to give us negative 9, right? Square root of 9 is 3. 3 times 3 is 9. And in the denominator, we're under a square root. So I'm going to multiply every term under the square root by 9. 9 times 1, I get 9. X squared over 9 times 9 is just x squared, right? The 9's divide out. So this is the answer we want. One more example. So for this next example, let's say that we want to know the derivative of arc cotangent of the square root of x. So again, no derivation necessary. We are just going to go right to the derivative form for arc cotangent of x, which is negative 1 over 1 plus stuff squared. In this case, the stuff is the square root of x, and we have to multiply by the derivative of stuff. And if you remember, this is just x to the 1/2. So we can use our power rule to take its derivative. So you'd get 1/2 x to the minus 1/2. Put differently, that's 1 over 2 squared x. So we don't have any weird fractions going on. It's not a big deal if there's a square root in the denominator, contrary to what your trig professors told you, because you had to be able to recognize unit circle values, right? But my final answer then, just doing a little simplifying, is negative 1 over 2 square root x times 1 plus the square root of x squared, which is just x. And there we go. If I wanted to know, say, the slope of the graph of arc cotangent of square root x at a point, all I would have to do from that point is plug x into that derivative I just found. Right, so that's inverse trig derivatives. Those derivations were really just to show you why the forms are what they are, and you can feel free to verify the ones that I didn't go through, and if you have any questions, you can always email me. But yeah, inverse trig derivatives, all done. Happy mathing.